everyone, my name is Renee. I'm with the University of Windsor, and today we're going to discuss the use of conjugated polymer nanoparticles to target and treat ependymoma tumors. So we'll begin by giving some background information and defining the problem. So ependymoma are rare primary tumors of the central nervous system. They are classified by the World Health Organization as a grade 2 tumor, defined by low survival rates, and they're common in children. Due to the rarity of this disease, it is difficult to perform large-scale clinical trials, which makes it very difficult to test new treatments. The current standard of care is radiation and surgery. Chemotherapy is not considered a better treatment as of yet. However, even though the ependymoma can occur in any part of the brain or spinal cord, they often occur in the cerebellum. This makes it very difficult to fully remove the tumor, as it's a challenging area to reach through surgery. And there's also a few limitations that we wish to address in our proposal. So to begin, radiation causes many unpleasant side effects. So we know it causes vomiting, nausea, and decrease in bone marrow density. These are all especially detrimental in children. It also has a lack of specificity. So radiation often targets the tumor cells, however, it also attacks the healthy cells adjacent to them. This is something that we hope to address with our proposal. Current treatments also cannot pass the blood-brain barrier due to size and drug delivery. And as mentioned previously, it is invasive and so it is challenging to remove this tumor due to its location and size and sensitive tissue area around it. So due to these limitations, there is a need for a novel technique to effectively treat the ependymoma tumor, and thus we propose the use of conjugated polymer nanoparticles. So now, what are these CPNs? They are made from organic high-conjugated polymers that currently act as semiconductors in organic electronic devices. These conjugated polymers undergo nanoprecipitation methods to form nanoparticles. Due to their synthetic ease, they have many properties that are desirable in biomedical applications. Some of these include the fact that they are longitudinally active. They have intrinsic fluorescent properties that are able to have emission and absorption properties over the infrared and UV region. They have a controllable size. Currently, we can engineer them to be as low as 80 nanometers. They can also be engineered to be biodegradable and non-toxic. This is important in the human body as it allows them to be excreted through normal metabolic processes. This is a feature that metallic quantum dots often lack. They're also electrically conductive. This is our main point. They're able to go through repeated cycles of heating and cooling to attack the tumor cells. And they can target specifically. So these can be easily tuned as we are a chemistry-based group. They can be engineered to specifically target only tumor cells and not the adjacent cells to the tumor due to the receptors on the ependymomas. Now there is research being done currently on nanoparticles, but it is very preliminary. Currently, one field of interest is imaging and diagnosis. An example of nanotechnology is quantum dots. They have been used, but they are considered harmful in the body. This is where our conjugated polymers come in, as they have excellent photostability, they have a low cytotoxicity, and they're easily modified, which allows us to be able to tune them to the human body and for specific imaging. Nanoparticles are also used in drug delivery and cell therapy regulation. However, in both these cases, they lack specificity. In a study done by Park and Group, it was determined that over 95% of enriched nanoparticles that currently are being used end up at sites other than the targeted tumor. Our benefit is as chemists, we alter the side chains and the surfactant to make this nanoparticle highly specific to the ependymoma tumor. And then, as mentioned previously, because of the fluorescent properties, we can trap this nanoparticle in vivo. Finally, there is very little research on radiation therapy using nanotechnology. So it's been briefly studied, and as we know, radiation therapy is a popular remote cancer therapy that induces DNA damage. However, it does cause severe side effects to the adjacent cells to the tumor sites. Current metallic nanoparticles are one of the most common anti-neoplastic drugs. However, the therapeutic effect is limited. And that is where our conjugated polymer nanoparticles can prove advantageous with their desirable properties, as mentioned previously.
So our conjugated polymers, the goal is to improve imaging, increase the precision of current cancer treatments, and also drive innovation in the field of electrotherapy. By doing this, we will alleviate the need for high-risk, invasive treatments in patients, thereby increasing their overall quality of life. So our project has 3 aims. The first is to prepare and design nanoparticles which are able to pass through the blood-brain barrier and specifically target ependymoma cells. Secondly, Secondly, we want to test the bioavailability and selectivity of these nanoparticles to the ependymoma cells. And lastly, we want to test the impact of these nanoparticles as intracerebral electrodes in electrotherapy. So the design, synthesis, and preparation of these nanoparticles consists of 3 parts. The first is the design of the conjugated polymer core. For our systems, we are using iso-indigo-based polymers. This is because iso-indigo has been shown to have very good stability in biological conditions, and also it is a polymer that is very extensively studied for its electronic properties. Additionally, iso-indigo is very easy to synthesize, which allows us to optically tune our nanoparticle. Secondly, we want to choose a surfactant molecule. This is chosen based on biomarkers of the target cell. In a study done by Armstrong and colleagues in neuro-oncology, shows that over 75% of ependymoma tumors overexpress the ERBB2 kinase receptor. This makes it an ideal biomarker for our nanoparticles to target. Consequently, we have chosen benzimidazole and kinidazole derivatives as our surfactant molecules because these have been studied to bind with high affinity to the ERBB2 kinase receptor. Lastly, we want to control the size of our nanoparticles. We can do this through nanoprecipitation techniques, getting the size below 80 nanometers, which allows it to pass through the blood-brain barrier. Secondly, we want to evaluate the bioavailability and selectivity of our nanoparticles in systems. To evaluate the selectivity, we will be performing a comparative analysis of cell size. We will be doing this by tagging cells with the ERBB2 antibody, and then we will tag our nanoparticles with fluorophores. This will allow us to visualize how well the nanoparticles are targeting the ependymoma cells while leaving healthy cells intact. Secondly, we want to determine the bioavailability of our nanoparticle. This would be done by screening a library of nanoparticles using a zebrafish model. So 72 hours post-fertilization, we will be injecting dyed cancer cells and nanoparticles into a zebrafish embryo. This will allow us to quantify the distribution of the nanoparticles during different developmental stages, while also being able to track any neurological, developmental, or cardiac disorders that may arise. Lastly, we want to evaluate the impact of nanoparticles as intracerebral electrodes for electrotherapy. This will be done in vitro and in vivo. So in vitro, we will take a mixture of the cell culture and the nanoparticles and plate them in wells. Following this, one well will serve as a control where no electric current is applied, and a second well will have an applied electric current. The nanoparticles, due to their electronic properties, will amplify and direct the electric field onto the cancer cells, inducing cell death. The effectiveness of this treatment will be tracked by monitoring cell death and cell proliferation rates. Similarly, in vivo, we will inject the nanoparticles into the site of interest. For us, this is the brain. Following a similar treatment, one of the subjects will act as a control, and the other subject will be subject to an electric field. Again, we will track the success of this by monitoring cell death and cell proliferation. So as a result, we will be creating a treatment that is non-toxic, highly specific, able to permeate the blood-brain barrier, and minimally invasive to the patient. This combination of characteristics is unheard of in brain cancer treatment. We truly believe that nanoparticles can revolutionize the way we treat cancer patients and also drastically improve their quality of life. We have great confidence that further investigation into nanotechnology can really change the way that we treat cancer research for the better. Thank you very much.
Again, do you think this should this prove viable? Do you think this would replace or complement existing therapy?
We think it could do both. The goal in the end, I think, is to replace existing therapies. However, much of the research is very preliminary. So right now, it would be an option to replace primarily radiation therapy because radiation therapy is quite toxic to the body. But since we are using electric fields as opposed to something like gamma radiation, it can significantly reduce the toxicity and also reduce the side effects since these nanoparticles are engineered to target specifically tumor cells. So it would reduce the damage to surrounding healthy tissue.
Are you aware of the side effects of electric field?
We have tried to do some digging into electric field therapy. It is a very new field of research. So we haven't been able to find anything at the moment that indicates any outstanding toxicities. We are actually, our research group is working in collaboration with the HEB group at Western, and they are currently conducting the tests on electric fields using GBM. So our goal would be to in turn apply this to Ependymoma, and this would allow us to monitor side effects that may come up.
People are being hard on you, Adam. The radiation therapy has side effects and you must replace it. But the thing about radiation therapy is it actually works. Do we know there's some controversy about these electric fields? Do they actually work? What is your reading around that? Do you know? First of all, the hardest question is how would it work?
So from what we've read, so we'll go back here. So basically when you apply an electric field, because the nanoparticles have semiconducting properties.
Well, let me stop you
Yeah.
before we get it. So forget the nanoparticles.
Okay.
Electric fields are now given, they put these electrodes on people's
Yeah.
skull. Have you seen that?
Yeah.
There's no nanoparticles there.
Mhm.
And the feeling is that it can help control brain tumor growth.
Yeah.
And then the HEB group is putting actually electrode in.
Yeah.
But the question is why would an electric field affect a brain tumor?
So that's actually pretty interesting. I did find an article, the current mechanism of how electric fields actually kill cancer cells is not completely understood.
Good answer.
Yeah.
That's correct.
Yeah.
If you'd have given me an answer, then I would have been
Yeah,
very surprised.
I did find an interesting study. They're testing the difference between like cathodes and anodes and like how do these different things affect the cell death. And they found that cathodes actually produce better cell death results. But again, we mentioned like this, it's really new. So
It's really new and it's still somewhat controversial as
Yeah.
to how effective it actually is and
Yeah.
whether a person would have to
Yeah.
have this field for the rest
Yeah.
of their life.
yeah, well the hope is like with the nanoparticles, we can eliminate that imagery that you gave us of the electrodes in the brain. So this is actually like replacing the electrode due to their electronic properties. So then they're within the body, and then they can amplify the electric field in the body because the dosage given is only about 4 volts. So it's a pretty low voltage, but once it's in the body, it can amplify it. And then because we're using isoindigo-based polymers, these can be naturally processed by the body to break down and excrete the nanoparticles when they're no longer needed.
Yeah, I actually have a similar question as Dr. Legacy. I don't quite understand how this works. Because you think of radiation or chemotherapy, they usually targeting cells because cancer cells, they are proliferating very quickly and then they're targeting the mitosis and all those. Yeah, I don't know why. Okay. And actually, I want one detailed question about your experiment design. And how are you going to deliver to a zebra embryo of this?
I think it's just injection. So our research group is primarily a chemistry group. So we're actually working with the Porter Lab to develop this. So they're the ones that developed the zebrafish model. So from what I've read, it's simply just an injection into the embryo.
Okay. So it's not specific to central nervous system.
Yeah, I'm not sure.
I think Lisa Porter uses zebrafish for many things.
She does.
Anybody's in the world authority on zebrafish, it's her. So there's probably some way to get it into the nervous
Yeah.
system.
And again, they're also testing this on
Like how
GBM.